Okay, so today this is going to be kind of boring. There's no doubt about it. More Dirac notation. And once you get used to this stuff, it's really easy. And I'm going to introduce this via the Stern-Gerlock experiment. And I talked about it last time. I'm going to draw it in a different direction. Hope the pen is about to die. It should be near the end. So this is what the settling flame looks like. And there's Ag atoms. So where I went to grad school, there was a lot of gas phase research groups, which is just not done anymore. And it's not done because it's very expensive and very esoteric in terms of the knowledge learned, but very fundamental. So that's why physical chemists are kind of upset that you just don't see this stuff done anymore. And a lot of that has to do with expense and the fact that kind of politicians have gotten a little overly involved with science funding. Like I have to write a broader impact on my grant applications, which is a description of how it actually is a code word, but anyway, I won't bore you with the details. It's why my research impacts society, anyway. Okay, so, anyway, the gas phase stuff has become unpopular, but getting things, well, if none of you are joining in analytical, Kelowna, Hanley's group, getting things into the gas phase is actually, can be freaking nightmarish, and like all the mass spec methods you hear about, most of those acronyms have to do with the source of how you get the material into the gas phase. So anyway, so I've learned a lot about it, but I'll never actually use it. So this is the Stern-Gerlock, and now the reason that you have this weird magnet is that you need some asymmetry in the direction of the field, and I'll explain that in a minute. And of course what you're going to do is you're going to look here. Okay, it's just like I said last time. Okay, and I talked about how the silver atom is closed shell, but sorry, it's not closed shell. It has only one non-paired electron in the neutral state, so that's pretty useful. Okay, so let's just say it's Ag and it has just a single electron. It's like Dr. Manhattan. It has a single electron. The magnetic moment off Wikipedia is a bunch of constants, which all would be 1. If it wasn't, if we use what are natural units, there would be no constants. S is the spin. So recall that spin is a type of angular momentum of the electron. So spinning charges have their own magnetic fields. Spin is a type of angular momentum. It definitely makes the electron a little bar magnet, but we don't know really what is physically happening. We do not think that the electron is like a little basketball that's spinning. There's lots of reasons to believe that, and it has to do with the fact that protons have the same spin, but are 2,000 times more massive. A spinning proton with a greater mass would not have the same magnetic moment as an electron with 1/2000th the mass, unless it's spinning at exactly the right rate. Anyway, so it's just weird. So no one knows what it is, but it makes it magnetic. Okay, so that's the magnetic moment. And the interaction energy, which I'll call U, I'll spell it all out so you get confused with my acronym. Interaction energy, and even though that would be U, that's an internal energy. I told you I was supposed to teach stat because I'm better at thermo than quantum, but anyway. Is that magnetic moment with the field, and the force on that. So we need a force. Help if I know how to spell. Force is, as always, minus the derivative of, usually potential, but whatever, energy, minus the derivative with respect to z. So now you see that there's no force unless you make the field slightly asymmetric, and that's why you have kind of this funky looking magnet. Okay, so what you expect out of this damn thing is if you think of the atom as a little bar magnet, so there's a north and south. Let's say that this gets deflected up, but some of them will be pointed down, so it gets deflected down. But sometimes they're like this, and it would just go straight through. So you would expect, what you do is this: you actually just put a glass plate, and you could just see the intensity of the reflection. It'd be unbelievably simple. So you'd have a plate, and let's just see what the distribution is. So that's what's expected. And what you get is, of course, completely different. And this is the experiment. Okay, so that's weird, but that's what you get. Now again, it's as though, so this is going to be, I hope that as I develop equations, you just kind of roll with the equations. But this is really, truly bizarre, because it's as though the atom's electron is either this or this. It can only be one or the other, right? Now, because I said if you had this, if it's a little bar magnet, again, like you played with as a kid, right? And I'm just holding it, north and south, right? They're often labeled of the toys you had as a kid. So it's like this doesn't exist. Here's what I'm going to tell you, this does exist. You can still have magnetic moment in the z direction or even the y direction, but it's not going to manifest itself this way. So, yeah, now in terms of my explaining it, I can't. This is fully a quantum phenomenon for which we have never nor will ever experience an analogy in what we call the classical limit, which is where we live because of our large masses. So, when I say that the magnetic moment is up or down, that's only in the z direction, and that's only we're measuring, but that doesn't mean that it doesn't also have magnetic moment in x and y. I don't know what they are because I'm only probing in the z direction. So maybe try not to think about that too much, because if you really start thinking about it, it really gets nuts. And basically all I'm describing is where is a vector pointing. And I'm describing things that are completely antithetical to everything you've ever learned before, but this is what we measure. Anyway, I got to point that out because that's what's happening. Okay, now what that means is that we have, you can measure how much spin you have, and look at this, you get this. So either it's pointed up, and you see I can measure the. What the hell is this? This is a magnetic dipole? Magnetic moment. Okay, this is the magnetic moment. So we can look at the distribution and figure out the magnetic moment. And this is how you can also figure out what h bar is. So that's clever. Let's see. Okay, so there you go. That's really all there is to say about it. This is unbelievably weird, but that's what you get. Okay, now we're gonna. I'm gonna draw this differently. So here's my incoming atomic beam. And I'm not going to draw all that magnetic stuff again. I'm just going to call it a Stern-Gerlock device. It'll be in the z direction. And out comes plus, and out comes minus, but there's a block. So I block. And so again, there's not much to say here. So I'm going to do some tricks. And we're going to have to develop a model to explain those tricks. And guess what that model did? And I'm showing you quantum mechanics in the process. Question?
What does S stand for? S at plus and S at minus?
Wait, this?
Oh!
Yes, this
yes.
Okay. Yeah, in the z component. So S would be composed of Sx plus Sy plus Sz. And again, the thing that is killing me is that it's saying that this is just up and down, and so there's no way it's not just pointed in the x or y direction. I'm telling you it actually is, but you're still. So what you can imagine is if I had simply rotated this 90 degrees, and that would just call that Sx, you would have seen that Xx is either up or down. Y you would have seen Y is actually kind of difficult in this geometry because it would be, one's like this, Y would be like this, and I can't really do that because the beam's coming forward, but you can imagine if somehow I could rig it up to work. This is either up or down by h bar over 2, again, this is up or down by h bar 2, this is up or down by h bar over 2. It's not like vectoring out to be, you know, if the magnet goes through this just the right way, it should just go straight through. But that's the one thing that will never happen. So that's why this is so freaking weird. Anyway, okay, now what you can do is put this through another magnet. Don't put that in the z direction, and what comes through is just plus. Okay, so this is a double Z, and it makes perfect sense. So, no information lost. Now, what that means, I'll explain when I draw a different one. Now, remember that the force of gravity does not affect things. Gravity is an incredibly weak force. And I don't know of, I think there are some examples of chemical phenomenon due to gravity, which would be like atmospheric type chemistry stuff. The way certain like isotopes will partition themselves in certain strata of the atmosphere anyway, but we're not really worried about any of that right here. Okay, sorry. All right, let's do it differently. So we're going to now put that in the x direction. Okay. So I just turned this magnet and I just turned it 90 degrees, right? It's not hard. Remember, gravity doesn't distinguish x and z. Okay, now, what comes out is plus and minus. And just remember, that's Sx, that's minus. Okay, what you get from this is, therefore the population is in, actually this is what I was saying just a minute ago, that there is in the z direction, there is a plus. All right, so we've captured, there's obviously a z plus population, and it is hanging out with some xx plus, and there is some, there, with my SC plus, there's also some xx minus. Okay, so be a little careful about this because there's a lot of permutations. I don't want you getting confused. What I'm saying here is that, all right, remember I've isolated SZ plus, right? That's SZ plus. SZ minus has been killed off. Not that it matters, but I have to stick with some kind of label system, right? Now, so that's why you see SC plus in both of these. With these SC pluses, some of them, in terms of x, were up and some were down. And half were up and half were down with respect to x, in that half that was up with respect to z. I know it gets to be a bit of a mouthful. Okay, now this is, again, not too strange, aside from the fact that it's kind of absolutely up or down. Again, that's weird, but we're not going to think about that too much. So now we're going to do something really weird. Let's see, certain Gerlock, Z, we're still going to, let's see, plus, we're still going to kill off the minus bar magnets, and that's killed off. Now we've got our X component, and guess what, we're going to kill off the, the negative in the x direction. Okay, then we're going to add one more, and we're going to do that in z, back to z, and the SOD completely messes with us. You now get plus or minus again, right? And it's 50-50. Okay, so we wiped out the negative polarized, the ones pointing down, but this turns out, remember before we stopped here, and it turns out though, it's actually screwing up the Z. So, so what this does, destroys the Z polarization. Now this is a statement that you probably heard in middle school, high school. Quantum mechanics says you can't measure something without perturbing it. You've heard that? You measure something, you destroy it. I don't know. There's variants of that. But that's a manifestation of this. You may have also heard. So you're also seeing the uncertainty principle. The uncertainty principle is kicking in, and we're getting to that. I haven't covered that yet. I hopefully you know what that is, but from your undergrad. But if not, we are going to cover that further. SZ cannot be measured simultaneously. And again, I've mentioned this before. People have tried to develop clever tricks, devices, machines that will beat quantum mechanics, and they fail every time. Einstein, Podolsky, and Rosen had come up with something like this with electrons. It's not quite like this, but it was similar. And they said, it involves atom smashers like the Large Hadron Collider. And they said, well, if you build a Large Hadron Collider type thing and make this measurement, you would see quantum mechanics doesn't work. When we built things like the Large Hadron Collider, not that one, but once we built atom smashers, we actually did it's called the EPR test, and they were wrong. So that was funny. Okay. Now, I want to point out that there's actually a classical analog. Well, kind of. It was light. Although I think what we've seen is that, remember, when on day one, I started using Maxwell's equations, and I showed you Maxwell's equations predict waves, right, for electromagnetic radiation comes in the form of waves. And if you recall, later we were able to derive things like light has momentum from just Maxwell's equations. So there's a little bit of the theory of relativity operating in there. So maybe light is trickier than we think. Maybe it's not as classical as we think. Let's see. Let's look at light. And maybe you've done this in middle school or high school. If it's X polarized. Okay, again, you hopefully learned this as an undergrad, that the electric field is going to have some strength. It's in the X direction, and it's of course a wave. You've got to let it vary in place and time. It's got to vary in both place and time. Y polarized the field. Remember that you observe the square of this, by the way. The intensity, which is what you would see, is the square of the electric field. And that comes up in various times and places. Okay, so they're basically the same. Okay, so what that means is I'm going to take a wave. Okay, let's say that's X. Let's have Y. I hope I did that right. Let's put it through a polarizer. And out comes only this one. I hope I did that right. And then you put it through a 90-degree polarizer. And nothing. 90 it's a 90 degree. Right. And you probably did this as a kid, right? Oh, by the way, 3D glasses in movies. When I was really little, and back in the 50s up to when I was little in the 80s, they used to have 3D movies, and they put those old 1950 3D movies on TV, and I think you know what I'm talking about, right? There's like a green and red shadow over the characters, and I don't know how they do that, but you have green and red filters on your glasses. it turns out that that's just designed to kind of give you two slightly different, your eyes perceive two slightly different images. That's part of it, and also you naturally perceive, I think, red is closer than blue. That's because the sky is blue, by the way. Things that are far away have sky between you and it, and they appear more blue, so your brain interprets blue as further away. Okay, the way they do it now, polarized light. So if you get your movie glasses, you actually have little light polarizers on them. So, okay, now again, you learned this, you hopefully did this in middle school, right? Okay, now I'm going to do a little trick, and of course it is coming out like this, but now I'm going to put in .45-degree polarizer. Now what? What do you think? Have you done this? I did this in high school. You know what happens, right?
In the components.
What?
This picture.
Yeah. It's weak, but light comes through. Okay, so that's weird, right? And this is what we're doing with the Stern Gerlock. So it's just that, I'm sometimes in all my classes, I'm kind of counting on maybe that you had some similar experiences as I did in high school. Because I remember doing this in high school. Because, as little kids were wowed by this, and we hadn't had polarizers. So the reason is that when it comes out of the 45-degree polarizer, it's actually, it comes in with all polarizations. It comes in like this. A 45-degree polarizer turns it like that, and now it has a component in the up direction. And I'll draw that. Let me draw that so that it's a little bit more clear. I'll even write some equations for it. Your book mentions this as well, but I know the book really jumps between being understandable to massively incoherent, and this is one of the areas I thought was pretty incoherent. Okay, so let's call this like how do I want to do this? Let's say this is like x. Let's call this x prime, and then let's call this like y. All right, so an x polarizer and then a y polarizer does nothing, but if we turn it at 45 degrees, let's call this coordinate x prime. Okay, now let's look at this. Now let me do this visually and then I'll do it mathematically. So x and y, and you started out the first polarizer did this. Then the second polarizer the 45-degree one does this. And notice then that you've now got a projection. You've now got a projection onto the y-axis. So it's not very intense, and we'll draw that kind of weakly, but it's smaller. But there you go. Little hats on these, I guess. Little hats. It means it's a direction anyway. So notice I drew the vector being weaker, but that's what's happening. All right. So. And again, I actually was going to try and find some polarizers. I was going to bring this in case you hadn't done this, but this is what happens. And yeah, there's really not much to it. Again, it's like something you learn in high school. But now what I'm going to do is I'm going to translate all of this phenomenon into Kets. And then we're going to learn to manipulate how Kets, the rules for doing math with them. And we're going to design that such that all of this is described correctly. So that's our goal. And we're going to spend about a month doing this. Because what you're really going to get out of this is the fact that quantum is really it's really statistical mathematics. Right? Variance and covariances and all that stuff. That's really what quantum mechanics is. As I mentioned, the Kets are going to be shortcuts, mathematical shortcuts to an unbelievable extent, but their underlying mechanisms are statistical. And up and down is a really good way to do that. Okay, so let's define the state Kets in the z direction. So I'll call them SZ and plus, and SZ and minus. Okay. Now I can go ahead and tell you, and I want you to get used to the terms that you hear constantly in quantum. This spans all space. This spans all Hilbert space. Now what that means is that, all right, in terms of like the Stern-Gerlock, the X guy, there's either up or down, right? So, duh. All right, there's nothing else to talk about. So, spans all space. However, maybe one of you would hopefully say, no, what about X and Y?
What about
Right.
X and Y?
Yeah, what about X and Y? I mean, where's X and Y? So, I might jump and say, well, actually, these don't span all space because I don't, how am I going to describe X and Y when those are Z? It turns out it does span all space because I can write X, the Ket like this with an X instead of a Z. I can write them as functions of this. So that describes X. I can do that for Y, and that means that these are all I need to describe everything. In fact, it's actually kind of necessary to describe it, and I'll call this a basis set. So I'll do everything in the SZ basis. And remember, these letters are arbitrary. I could also do this in the X basis, but I'm just going to choose Z because we humans tend to think of Z as special because of gravity. It's obviously not for the reasons I've said. Okay, now in terms of spanning all space, that means I've got to be able to do Sx plus. Now, for reasons you'll see, I'm going to design this way, and the reason is because it's going to do all this stuff that I just described. This description I'm writing is consistent with that. Now, as for why that is something I'm going to prove, but it's going to take me a while, right? The point of this is to learn Ket mathematics. And so I'm going to proposition that it works this way. Oops, minus, okay, SC plus. So I'm proffering the potential for this to be a description of X, and then I'll come up with one for Y, but let's just worry about X first. So, Kets are states. I contend that these span all space, and that means that not only do they describe what's going on in Z, but they also describe what's going on in X, and we'll get to Y in a moment. So notice that I've got a description for everything, and I'm only doing it with SC plus and SC minus. Now, again, as I'm going to talk about in a little bit, once we get to more Ket mathematics, this description will describe all this stuff I just showed, and that's why I'm saying this is correct. It's going to take a little bit of time to get there. Now, what you can do, of course, is some algebra. And you can find that you can put SZ in terms of SX, and it looks about the same. When you're doing these problems, the only thing that's kind of difficult is not getting confused, not getting your pluses and minuses confused. You can't do that. You won't get the problems right, obviously. Hopefully I've gotten it right. So anyway, so again, another reason why we can say that we span all space is because we can write everything in terms of everything else. So what you have to do, and especially with these spin systems, you have to pick a basis and stick with it. So a lot of your later homeworks, actually I think on your present homework, which we'll worry about later, you're going to be transforming between one representation and the other. And it's something that you really need to learn how to do because it's a very common thing. Let me tell you, let me foreshadow what you're doing. Especially, there's so many of you who are material science type people. we think of wave functions as having a position representation, like a px, a py, and a pz orbital. But when it comes to materials, you can't think of it that way. It fundamentally doesn't work. You have to think of them as momentum type of wave functions. So what I want to get you to do is getting used to the fact that I can turn a representation of a state into a different type of representation. And learning how that you can do that and how to do that is what one of the points of this section is. Although we won't really get to anything there for some time. Okay, let me do SY. Okay, now my understanding is that this is one of the reasons that imaginary mathematics was discovered and people realized its value is, hold on a second, let me see where I'm at, is because in 3 dimensions, people realized that, what have I done? Just making sure, yeah, okay. I wasn't sure where it was in my own notes. Is that on these simple spin-up, spin-down systems, you have to have a third. So, you know, if you look at this, so SZ is SZ. Forget this guy for now. I've got SX plus is plus SZ plus SZ minus. The second one is I've got minus SC plus SC minus. Let me make sure that's correct. Yeah. Okay, so in terms of games with plus or minus, so I've basically added the 2 SC functions and then I've subtracted the 2 SC functions to give my SX functions. So now I've got to do some kind of trick with SZ functions to generate Y, but the Y's have to be different than X. And that's like, well, what the heck else is there? What's left than adding and subtracting, right? That's the only real combination you can do. That's true, but here's what you do. And as, you know, as I alluded to, this is one of the reasons people realized that you needed complex. Did I say X? That's Z, right? We're in the Z basis. That you you have to have complex numbers to have 3 dimensions and have things like spin up and spin down. Sorry, why am I obsessed? I'm obsessed with X now, I don't know why. Let's see, plus, minus. What the, I see what I did. And then we got minus I over the square root of 2, SZ minus, there we go. Okay. Now the point of this is that they're distinct, and by distinct they're orthogonal, and we'll be doing orthogonal here in a minute. Okay. Now a lot of your homeworks are going to be designed to deal with an arbitrary state. So these guys, these are like pure. I would call them pure states. They're a little too perfect. Life isn't going to give you such an easy setup. So when you don't know what you're dealing with in terms of your experiment, you're going to have some kind of state that you don't necessarily really know what it is. And I'm going to represent that this way. A state where there's some weighing factor of plus or minus. Right. So of course, not having set what the C's are, then they could represent that. Okay. Now the next thing I want to get you to do, now I'm going out of order in the book on this, but I want you to see this right now. When you're doing homework problems, when, a lot of times to understand how things work, I like to write things out as Kets. Plus a Ket, minus a Ket. And the more we get into this, the more it's easy to kind of visualize what's going on. You're going to get used to this and you'll kind of internalize it quickly. However, when I have you do deeper mathematical analyses, like on your homework, you do not want to do it this way. You can, but some of the problems, if you really know what to do, it'd take you 5 minutes to like write it out. And that's if you know what you're doing, so it'll take a little longer. Let me give you another way to do this. So So again, I'm jumping ahead. I just want you to make sure that you don't get completely combobbled on your homework. You can represent these as matrices. And so when I have you do a bunch of operations on these states, it ends up just being a bunch of matrix math, multiplying a matrix times a row or a column vector, which is relatively easy, especially when your column vectors are this. Right, so you can see that's the SZ plus and that's the SZ minus. So of course you know that SZ minus is of course 0 and 1. Right, so hopefully it's just kind of automatic. You look at that like, yeah, I get that, right? Okay, that means Sx plus, I wrote plus for some reason, is 1 over the square root of 2. So remember when you see that in a matrix, a number outside of the matrix, well again, this is a row vector, you multiply that number by all the internals. It's supposed to be common there. And 1 over the square root of 2. So this is kind of consistent with that minus sign that's right there. So you can see that I'm representing these the exact same way. And again, I want you to see this because on your homeworks, when I have you do a bunch of operations, there's 2 ways to do it, but when you do it with matrices, it is unbelievably easy. What's wrong with my handwriting? 2. There you go. Okay, a convenient way to represent these. I'm not gonna, I'll bring these up more tomorrow, but anyway. So these are very convenient tools for doing problems. And I will show you sometimes in class, but more so in your homework. Okay, now I also want you to remember that, let's see what I want to do. Okay, so let's start, what I want to do is start mimicking the I want to start mimicking the Stern-Gerlock experiment. Okay, so what I want to do is, whether I work with this representation with matrices, or I'll generally stick with these in class, I want to figure out how, like, the SZ plus was turned into SX, which simultaneously messed up the SZ polarization, right? I had SZ going into the SX, SZ plus, but what comes out, the SZs were mixed up. So how does that work? All right, so let's see here, how do I want to do that? So what I want to point out is that we had a situation with this stuff where the Stern-Gerlock device turned one state to the other. And we're going to do that with an operator. Now, you've all had undergrad quantum, and you know operators are like the momentum operator. It's the derivative. It's just the derivative with respect to x, minus h bar, and minus I h bar. But anyway, in this case, this operator is going to turn one state to another state, because we saw the Stern-Gerlock do that. So let me actually draw that, because that's when you and I get a little confused. So Sx plus, and let's say that was a wave like this. Hopefully I'm drawing that okay. Stern-Gerlock experiment in the z direction. And there's a block on it, and what's left is the SV plus. Okay, I should have drawn this before. I didn't mean to accidentally delete my the experiments I've done before. So maybe that's like this. Then, if I want to draw it like little photons or little wave functions. Okay, so we had a Stern Gerlock that did this. Maybe I should stick with how it was done before. So like here's the plus, SX plus, and then it just bothers me. I gotta get it just right or the world will blow up. Okay. So again, we had a Stern Gerlock experiment that took some prepared state. We made a measurement. We had a block, and then out came the SC plus. So my operator needs to basically mimic this device, this measurement device. So, there's only one thing about that. The one thing to learn already is that operators, and again, Hamiltonian operator, momentum operator, you've seen operators. You can associate them with measurements and the devices that make those measurements. Those are really the same thing. So you can think this as a mathematical representation of this bar magnet and some kind of beam block inside of it that does all this. Okay, now I've got some ideas of what Kets do. Now I've got to get an operator, and I got to turn this state into that state. Okay, now as I was blabbering on about matrices, let me show you a quick way to do that. Now what I've got to have is SV plus is this. SX plus is, oh, here, I'll put the 1 over square root of 2. I'll put it inside this. Okay, so what does that? Let's see, did I do that right? Yeah. Okay. I got to get those equal to each other. All right, well, matrix math says that to turn one column vector into another, you've got to have a matrix. And let's see, what would that look like? So I contend that it looks like this. And so this is SX plus. This is SZ plus, and this is, okay, now let's see if that works. Now, to do this, you gotta remember how matrices work. This times this, plus this times that go into the first element. So that's square root of 2 divided by square root of 2, that's 1. Okay. That's the first element. The next element is this times this, 0, 0, 0. Okay, so there you go. So that's our operator. And again, that's why I want to show you matrix representations. I want to show you matrix representations real quick. Okay, and I got just enough time. Now, that's the matrix way, and I hope you see that that's actually really easy. Now, let me do this with the Ket way. Always two ways to do this. You pick which one you want to do. But I can tell you that you're going to generally want to work with the matrix. Okay, now let's remember that SX plus is, I know it's up there, but I'll rewrite it. 1 over square root of 2. SZ plus, square root of 2. SZ minus. Now, what I want to do is introduce a bra, that's a ket. Here's a bra. A bra is like this. Now this is a projection. Okay, so a ket is a state, a bra is a projection onto a state. Now what that means is this. SC plus, so that is a projection onto SC plus. And if we project onto the SC plus state, we get the number 1. All right, now again, remember, what I'm showing you for the first time is how to interpret Dirac notation. Ket is a state, that's a projection. The way to read this is to say, how much of this state projects onto the SC plus state? Given that it is an SC plus state, it should fully project. All right, pretty simple. Okay. SZ plus, let's project the SZ minus state onto the SZ plus state. how much of this state is in the SC plus state when that original state is in the minus state? None, right? It's not. None of it is in that state. Okay. Now, because of that, because what I did here was I turned this into that, what you can basically do is figure out that, I think I'm going to, I may mess up some of these constants at times. Generally, people just drop the constants. Ket, bra. That is an operator in Ket space, whereas before it was a matrix. These are the same thing. Notice that SC plus is in the upper left quadrant, and then everything else is 0. Okay, now the reason that works is, oh God, where am I at? If you project onto Sx plus, what you end up with out in here, and in here, what you end up with is square root of 2 over square root of 2, Sz plus, Sz plus, Sz plus. Now I do the same operation on this term, plus square root of 2 over 2. Sz plus, here's the operator. Sz plus, and here's the operator. Sz minus, that's from the state. Little commas. Little commas. And the world will blow up. There we go. Now this guy goes to 0. This guy goes to 1. And you see what you get is Sz plus. Okay, so the operator defined this way with these Kets, which is my ending state, and a bra, which is a projection. You do some middle school algebra. You just gotta understand what happens when a Ket runs into when a bra runs into a Ket, and you've turned Sx plus to Sc plus. Okay, we're late. Sorry, gotta go. This is how it works, right? This is 90% of Dirac rotation. So next time we're just going to do more of this with XS, with plus and minus, until you're sick of it and you get it and you can do your homeworks, and then you're a genius. You understand stuff. All right. Okay.